Okay. In the last class, we are considering multiplication of two binary words, W bit words A and B, and how to get C. We followed Horner's rule. Okay, but then as an example, we took 4-bit words, okay, A and B, and we carried out the multiplication. There was a multiplication table, which is again I have, for your sake, I have rewritten here. So there was an array. Dependence graph was an array in which 4 bits A0, A1, A2, A3 they were coming parallelly through one side, and 4 bits of B, B0, B1, B2, B3 they were coming parallelly through another side. So that was bit parallel or word serial structure. That is, if the bits are coming in clock, like at nth clock, I have got a word whose 4 bits are A0L, A1L, A2L, A3L. That is in the nth clock, LSB, next to that 4 lines, 4 bits. Similarly, B0L, B1L, B2L, B3L. In the very next clock, L plus 1, bits will change. Here also bits will change for A and B both. And again, we carry out another multiplication. So, we will do multiplication again, clock after clock. That was the purpose. Now, we will consider another system where instead of it is bit serial, bit parallel or word serial architecture, we will have a bit serial architecture where bits of either A or B may not be both, either A or B, they will come serially in the system. Okay. There will be only one line through which first, because we follow the LSB first combination convention. So, A0 will come, then A1, then A2, A3 like that. Okay. We may consider situation like this, where suppose you are calculating a filter output yn as W0 xn plus W1 xn minus 1 and dot 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 dot. Consider any multiplication. This like A, this like A, this like B. This may be 16 bit, this may be 16 bit, okay, or 4 bit, 4 bit, 8 bit, 8 bit. Similarly, here consider this multiplication. Here you see data is coming. So, nth clock, if it is 16 bit, there will be 16 bit lines 0 1 0 1 0 1 0 1, that will be a 16 bit word in 2's complement form, but multiplied by W0, which may be a 16 bit word again, but that is constant, that does not change from clock to clock. So, here if you call that B, so all the bits of B they are time invariant, they are even fixed, okay, internally built in, and bits of A, that is a function of n. Okay, if it is 16 bit, all the 16 bits, each of them can take 0 or 1, 0 or 1, but at nth clock we will get one word, nth plus 1th clock another word. So, nth clock we will have one product, n plus 1th clock we will have another product value, and that we will consider this situation where one of the words is dynamic, it is coming against clock from outside, and that we take to be A, and the other one say B, it is built in. So, it is constant, it does not change with time. Okay. For our example, we again consider W equal to 4, this one, okay, this case where we consider 4 bits for A, 4 bits for B, all right. So, Lth, what happens when we convert word serial, that is bit parallel structure into bit serial. Suppose you had originally 4 bit lines in parallel, one for A0, one for A1, one for A2, one for A3. But now I have got one line, okay, through which I will first send A0, then A1, then A2, then A3. So, if this is one clock period, originally this was used and I had 4 lines. So, over this entire duration I had A0 on this line, A1 on this line, A2 on this line, A3 on this line, but now I got only one line. So, this clock will be divided into 4 parts. This clock. So, this is one sub clock during this time, okay. This is one sub clock. So, in the first sub clock I will send B0. So, B0 will come out first, okay. Then here I will send B1. So, B0 will be followed by B1, then B2, not B, say A, because B is built in. So, A0, A1, then A2 here followed by A2, then A3 followed by A3. A0, A1, A2, A3. Let me draw again. So, during this clock, we will send A0. So, through this line, A0 will be the first guy. Then here I will send A1, then A2, then A3. all right. So, if it is Lth, if it is Lth original clock Lth, so I had got 0th, first, second. So, Lth, that will have 4 sub clocks or bit clocks. So, this will be 4L plus 0, then this will be 4L plus 1, then 4L plus 2, 4L plus 3. So, in 4L plus 0, A0 will come out, then 4L plus 1, A1 will come out, then 4L plus 2, A2 will come out, 4L plus 3, A3 will come out. Then again from Lth clock, we go to L plus 1th clock, but all the 4 bits again come through serially through one line. So, again L plus 1th clock also will be divided into 4 sub clocks, and through them we will send out, it will be 4 into L plus 1 plus 0, 4 into L plus 1 plus 1, 4 into L plus 1 plus 2, 4 into L plus 1 plus 3, and through them again we will send out new A0, new A1, new A2, new A3, and it will go on like that. So, it will be a bit serial system then. Okay. Now, keeping that in mind and keeping also this in mind that all the bits of B are built in, they are not changing with clock, they are built in constants. Look at this A0 here. A0 is arriving here at 4L plus 0. I am doing A0 dot B0, but not including it, not counting it, I am throwing it away. So, this is of no use. So, at 4L plus 0, A0 comes, I do dot, but then no use. At 4L plus 1, A1 comes. So, A1 dot B0, okay. And this I then at next clock at 4L plus 1, A2 comes, I do A2 dot B0. Then 4L plus 3, A3 dot B0, and then I sign extend it. And with A1 dot B0, what I add? A0 dot B1. A1 dot B0, I add A0 dot B1. Now, you see, if there is a line through these who are coming, A0, in fact, I should write A0 bracket L, A1 bracket L like that, but that L I am dropping, otherwise it will become very clumsy here. But actually, I should write A0 L, A1 L like that. That L I am dropping, but you keep that in your mind. Then A0 came at 4L plus 0 of no use, then A1 came at 4L plus 1, and then dot AND gate with whom? All of them AND gate with B0, A1 dot B0, A2 dot B0, A3 dot B0, A3 dot B0. So, other input is B0 built in, this is built in. So, what I get here is A0 dot B0, which I do not use, then at 4L plus 1, A1 dot B0, at 4L plus 2, A2 dot B0, 4L plus 3, A3 dot B0, right. Now, start with A1 dot B0, this guy. This is to be added with A0 dot B1, but A0 came here at 4L plus 0, okay. And I have to add with A0 came here at 4L plus 0. A1 dot B0, this is formed at what clock? When A1 came. When A1 came? At 4L plus 1. At 4L plus 1, I am having A1 dot B0. So, at 4L plus 1, I should also have A0 dot B1. That means, A0 which came at 4L plus 0 should be available at 4L plus 1 also. That means, I should put it in a delay. And then, I need A0 dot B1. So, now A1 dot B0 at 4L plus 1, it has come. This will get added with A0 dot B1. A0 came at 4L plus 0, after one cycle delay, it is coming here at 4L plus 1. So, at 4L plus 1, they will be added. So, there will be an adder, full adder, one minute. So, A0 dot A1 dot B0 at 4L plus 1, that time A0 has come, because after one cycle delay here. So, that when it is A1 dot B0, that time it is A0 dot B1, they are to be added with 0 initial carry. So, this full adder, I am giving a switch, through the switch it is touching here at what time? 4L plus 1, that time it is touching this. At that time, I have got A0 dot B1, this is a carry input, carry will start here, initial carry 0. So, this switch will touch it at 4L plus 0, sorry 4L plus 1, that is the time 4L plus 1, okay, that is the time addition is starting here. It will touch it at this point 4L plus 1, that is the time I am studying this addition. So, at 4L plus 1 A1 dot B0 here and A0 dot B1, they take initial carry 0, produces a result, produces a carry. This carry will be now moved here in the next cycle have A2 dot B0, A2 comes here at 4L plus 2. So, in the next cycle A2 dot B0 comes, that time A1 has moved here, A1 dot B1. So, A2 dot B0, A1 dot B1, they get added and with previous carry. So, this carry comes here with a delay. So, whatever carry got generated in this cycle, that in the next cycle moves here. So, if it is 4L plus 1, it is 2, I am not writing 4L again, it is 2, comma, so into 4L plus 2, I do the addition. Again result comes out, new carry comes. Then is A3B0, A3 came here at 4L plus 3, that time A2 has moved here. So, A3B0 and A2B1, A2B1 they get added with the previous carry. This addition is taking place at 3, okay, this is 1, 2, 3, all right. Again new result, new carry, but now I have to do the sign extension. A3B0 should again come to the this input, come to the adder input again, repeat it. The way this sign extension is done, we put it through a delay and move it here. So, it is 4L plus 1 is here, 4L plus 2, 4L plus 3. So, 1, 2, 3, during these occasions switch is touching this. Then at 4L plus 3 I had A3 dot B0, A3 dot B0 here. Then at 4L plus 4 it moves here. So, switch also moves here 4L plus 4. Remember 4L plus 4 is nothing but 4 into L plus 1 plus 0. So, for the L plus 1th cycle, the next cycle it is the 0th. So, it is that time A0, new A0 should come, because the L plus 1 is what? The 0th bit cycle. That time new A0 would come, but my switch is moving here, not here. So, new A0 times new A0 dot B0, even if it is formed here, that will not go into full adder. This will go into full adder. That is how we are ignoring this. So, this ignoring, that is how we are ignoring this. Okay. Now, this addition is done, addition is here. So, I am getting this result, this result, this result, this result. This is coming at 4L plus 1, but 4L plus 1, this will be discarded. So, 4L plus 2, that times A0 dot B2. So, A0 came here at 4L plus 0, it came here at 4L plus 1, now coming here at 4L plus 2. So, it is, and then AND get it with B2. You get FA full adder. So, what will happen? This will touch this at 4L plus, this I will discard 4L plus 1. So, 4L plus 2, 3, 4, 2, 3, 4, 4L at 4L plus 2, A0 came at 4L plus 0, then here at 4L plus 1, here at 4L plus 2. So, I have got A0 dot B2 and with adding with this result, that is at 4L plus 2. New result, new carry. This is the carry input. Again initial carry here, when you do this addition, initial carry is 0 and this addition you start at 4L plus 2. Okay. At 4L plus 3, A1 came here at 4L plus 1. So, it is at 4L plus 3 here, A1 dot B2 with this result and the previous carry, new result, new carry. Then this came at A2 B2, A2 came in at 4L plus 2, now it is 4L plus 4, isn't it? 1, 2, 3, 4, so 4L plus 4, A2 B2. So, this result comes here new result, new carry goes on. Then this carry again comes, but this result is repeated. So, this result will be repeated here. This is a sign extension. So, 2, 3, 4, it is at 5. So, 4L plus 5, and 4L plus 5 means 4 into L plus 1 plus 1. Okay, 4 into L plus 1 plus 1. So, for the L plus 1 cycle per word, bit cycle 1, okay, bit cycle 1, that would have come, but that we are ignoring. Okay, that we are ignoring. Like we, all right, that gets ignored. When it comes to 4L plus 5, instead of taking this previous result, we move the result here. Okay. So, whatever result is generated, that is ignored. That is how we ignore this result in this result. And now, last one, we put a delay again. So, A 0 came here at 4L plus 0, 4L plus 1, 4L plus 2, 4L plus 3. And you need an inverter because all are not gated. B3, once again you have got adder, full adder, carry. So, addition starts at what? This was at 4L plus 1, 4L plus 2, 4L plus 3, because this one we will ignore, 4L plus 3. So, at 4L plus 3, this previous result will move in here. So, there will be switch, it will be here at 4L plus 3, then 4, then 5, A0 bar, then A1 bar, A2 bar. A0 came here at 4L plus 0, here after 3 cycle 4L plus 3, followed by A1, followed by A2, followed by A3, right, and they are not gated. And when it comes to 4L plus 3, that time this result, previous result will be extended. Okay, 4L plus, this is 0, 1, 2, 3, 4, 5, 6. So, 3, 4, 5 here. When it comes to 6, this will move here. All right. So, this is the result, this is the previous carry. Now, here when you do the addition, this will be given as initial carry. So, initial carry will be neither 1 or 0, it will be B3. So, it will be B3 is 1, it will be 1, otherwise 0, and the addition starts at 3. So, it will be at 3. So, this is a bit serial adder, it is called Leo's all right. There are other forms of bit serial adders also, various. I will just consider this. This will give you an idea about what is meant by bit serial adder. All right. Our next topic will be, going beyond this multiplier. Why not take the whole digital filter itself and have a bit serial realization. That is the next topic, bit serial realization of bit serial realization of FIR and IIR filters. Here one thing we will teach, I will just touch upon, called canonic signed digit, CSD. Suppose we are doing this multiplication, if say B1 is 0, binary 0, then you see we know the AND gate result of any bit with B1. If B1 is binary 0, A0 dot 0 is 0, this is 0, this is 0, this is 0, and when you add no change, you get the same result, which means this entire addition step here can be skipped. So, if you have more and more zeros, this addition, intermediate addition steps can be skipped. which gives rise to a lot of saving in hardware. Similarly, if you go further beyond, see this array. Okay, what does the array do? Array, if you have got some of the bits 0, the entire operation here is not required. So, this row can be skipped. Okay. For instance, suppose B0 is 0 or say B1 is 0. So, B1 dot A0 which is 0 plus incoming, so incoming remains as it is. Okay. And carry, no carry gets generated, and same here. So, this 4 easily go away. So, you get some saving in hardware, which means if it is like this, that out of two numbers you are multiplying A, B, at least one of them has got many bits equal to binary 0, then your multiplication complexity will go down hugely, okay, because many rows in the overall multiplication table by Horner's rule will not be required, because you already know the result. No computation, no addition is required there, because nothing changes when you multiply your word by binary 0 and add with something incoming. All right. Therefore, why not do something so that one of the numbers multiplicand has lot of zeros. Now, here you can ask me the question that look, B is not in our hand, B is in the hand of the customer, whatever B is or your design, whatever B you get, you have to accept that. How can you say it will have lot of binary zeros? There, this mode of this canonic sign digit representation system, it is a data format, it is a way of encoding a number, okay, that comes in play. CSD, it gives you, instead of common binary system which gives you 0 and 1, that is conventional binary, you will have 0, 1, but CSD will give you three things: 0, 1 and -1. Okay. And using this, and that is why we call it CSD digit, because bit means only two possibility. Anything that has more than two possibility will have to be called a digit. So, that is why we say CSD digit, canonic sign digit, not bit, not canonic sign bit, not CSB, but CSD. But using this provision of having a -1 also, -1, there are powerful ways by which, given a decimal number, you can encode that into these digits, using these digits into a word which have lots of zeros. In fact, you can make sure that at least 50% of the digits in the representation are zeros. So, those zeros will not contribute anything in the multiplication. When it is -1, -1 times some number is nothing but minus times minus of original product. Okay. So, first you carry out the normal product having a binary 1. Whatever is the result, just take a 2's complement of that. That will give you the negative of that. All right. I am showing a way. Suppose you have 1, 11. So, I am not considering fractional number. For your convenience, I am taking full integers. 11, I can write like 16 minus 4 minus 1. 16 means, that is, if I have got 2 to the power 4 power, 2 to the power 3, 2 to the power 2, 2 to the power 1, 2 to the power 0. So, 5 digit word. So, it is 2 to the power 4, I will give plus 1. Then 2 to the power 3, 8, there is no 8 here. So, 0 into 2 to the power 3, 1 into 2 to the power 4. Minus 4 means 2 to the power 2. So, minus 1 times 2 to the power 2, see minus is coming. Then 2 to the power 1 means 2, there is no 2 here. So, 0 into 2 to the power 1, and again minus 1 means 2 to the power 0 is 1. So, minus 1 times 2 to the power 0. So, this will be the word. So, you see I have coded so that there are 2 zeros. In CSD, I mean it is always, I mean the coding technique is such that whenever you have got a non-zero digit, it is always guaranteed that the left neighbor and right neighbor will be zeros at least. I mean neighbors further to the left, further to the right also could be zeros, but at least immediate left, immediate right will be zeros. Here I have got only right, there is nothing in the left, and here I have got only to the left, nothing to the right. Here I have got both immediate left, immediate right, they are zeros. Take another example. say 18. 18 can be written as 16 plus 2 to the power 4. It is very easy, 2 to the power 1. So, this will be 1, 0. So, 1 into 2 to the power 4, 0 into 2 to the power 3, 0 into 2 to the power 2, 1 into 2 to the power this. So, you see here it has got two neighbors, left and right both are 0, or neighbor further to the left also 0. All right. So on and so forth. This way you can carry on. There is a powerful way actually. There is an algorithm by which this encoding can be done. But here purpose is this, that we can have plus or minus 1 and of course 0, but we can make sure that every non-zero digit has got at least 1 0 to the left, 1 0 to the right, which means approximately 50% of the word will be filled with zeros. At presence of the zeros, simplify my hardware, because when I do a multiplication, those zeros contribute to nothing. No, no hardware is required to do multiplication using zeros. So that gives rise to huge saving. So CSD is a powerful technique. When we go for bit serial relation of filters, we will assume that the filter coefficients have been given in CSD form, and then we will proceed. This we will do in the next class. Thank you very much.